Hi everyone, I am Rathish and I am going to present our work on low-span parallel algorithms for the binary forking model. This is joint work with Zafar Ahmad, Rezaul Chowdhury, Pramod Ganapathi, Gregory and Mohammad Javanmard. Let's start with some background of binary fork-join model. Binary fork-join model captures well modern multi-core shared memory systems. Computation in the binary fork-join model can be viewed as a DAG, where the root node represents the first instruction of the starting thread. Each node in the DAG has at most two children. If node U represents ith instruction of some thread and node U has two children, namely V and W, then V represents the I plus 1th instruction of the same thread and node W represents the first instruction of the newly forked thread. There is a join instruction that joins the forking threads here. Recently, Belloc et al. Introduced a new model called binary forking model that allows programmer to use atomic test and set instructions. So why there is a need of introducing new models such as binary forking or fork join model when there is PRAM model for a very long time which has many successful results? In the PRAM model, there are P processors which share a shared memory. The P processors progress synchronously in log steps in the PRAM model and then in constant time they synchronize. In the figure, in time step 1, all P processors compute in log step. In time step 2, they perform some computation and then synchronize in log step. Again, in time step 3, they perform some computation in log step and then synchronize in constant time. And up to the end of the computation, they perform computation in log steps. However, in real architectures, processors progress at different speed due to asynchronous events such as interrupts, cache misses, hyperthreading, overclocking, and many more. And because of this, it could happen that some thread progress this much, some thread might progress very less, some other thread might progress a lot, and that can happen at varying rate. Hence, the assumption that PRAM model makes that all the processor progress in log step is not true in real architecture. So we would like to design and analyze algorithms in a model that better captures real architectures. So here is a way to transform any algorithm from PRAM to the binary forking or fork join model while increasing the span by log P factor. Here there are P processors that perform some operations in log step in the PRAM model and then in constant time they synchronize. Each log steps of P processors is simulated using a binary tree of height P. So in log P time, all P processors can be synchronized. Let's understand this through an example of comparison-based sorting. We start with Cole's parallel merge sort in the PRAM model. In the PRAM model, the algorithm has optimal log n span and n log n optimal work. We need to transform this algorithm in the binary forking model by simulating each log step using a binary tree of height n log n. The span increased from log n to log square n. However, the works remains optimal, which is n log n. On the other hand, we can also achieve optimal log n span at the expense of increasing the work from n log n to n square. Here, each item independently computes its rank by comparing itself to all other items in order n time. And hence, in O of n square total work, we can achieve optimal log n span. So naturally the question looms whether we can achieve optimal PRAM bounds, both work and span simultaneously in the binary forking or fork join model. So for comparison based sorting, we want to achieve n log n work and log n span in the binary forking model. In this paper, we try to answer this question not only on sorting but other fundamental problems. Our major results are the following. For comparison based sorting, we present a randomized sorting algorithm that achieves optimal work and span both with high probability in n. For Strasson's matrix multiplication, we present a span optimal Strasson algorithm that achieves optimal span while increasing the work only by a log n factor. And we also present a work optimal span Strasson algorithm that achieves optimal work here but increase the span only by a log n factor. Using the techniques that we introduced for sorting and Strasson's multiplication, we also improved the bounds for first Fourier transform and other dynamic programming problems and convex cells. We also present space adaptive algorithms for stress and matrix multiplication and sorting, which always achieves a span within a log n factor of the optimal for any given amount of space. We now present our algorithm and analysis for comparison-based sorting. Our sorting algorithm has two major steps. In the first step, we sort almost all the items, specifically n minus small of n items. We sort them and we call this method as subset sort. And in the second stage, we incorporate the leftover small of n items into the already sorted list. Before we go on describing each of the steps, here is one important distinction between Belloc et al. Sorting algorithm and ours. Unlike Belloc et al.'s sorting algorithm, we do not explicitly use atomic distance set operations. Instead, we use a weaker primitive called queued concurrent write. In the queued concurrent write, if there are k threads that are trying to write in the same memory location, then an arbitrary writer among those k writers wins, and only that writer can write in the memory location and all other writers fail. And this whole queued concurrent write operation takes order k time when k is the number of threads trying to write in the same memory location. We now present the first step of our algorithm, which we call subset sort. Here all the items except little of n items get sorted. There are few steps in our subset sort algorithm, where the first step we do some sampling, then we do bucketing, then sorting, and then we get final output array. Given an input array of size m, in the sampling step, we first sample roughly square root of m times log cubed n items. Then we sort these sampled items, and then we subsample further to get only square root of m items roughly. This ensures that the subsampled items are evenly distributed. In the bucketing steps, we allocate square root of m buckets, each of size k, where k is this value. We then attempt twice to place each item from the input at a random location in its bucket. And since we are attempting to place each item twice, there will be duplicates. We then remove the duplicates from the buckets and we closely pack the items. After that, we go into sorting step, where we recursively sort each bucket from the previous step using subset sort. And if the recursion depth is already log n, then we perform a deterministic sorting algorithm by Kohler and Ramachandran using optimal work and log n times log m span. In the bucketing steps, since there is collision, some of the items may not find its place. Hence, at the end, we will get a sorted list of all the items except little of m items will be left over. We prove the following theorem for subset sort. Given an array of n items, subset sort performs in log n work in log n span, both with high probability in n, and uses little o of n log n space to sort all items except small o of n items with high probability in n. We now come to the second stage of our algorithm, where we incorporate the leftover small o of n items with the already sorted list. Recall that our original input was array A of size n, and after doing subset sort, we almost sorted all the items except little of n items left over. We call the sorted list of size n minus small of n as array B. To incorporate the small of n leftover items, we start with two input arrays. The first one, A, is the original input array, and second, B, is the one that we get as output from subset sort. We now describe the steps that we use to incorporate the little o of n leftover items as follows. After subset sort, almost all the items except small of n items were sorted, and we need to find out where in array B those small of n items will fall into. Hence, we create mod B number of buckets, and we distribute s units of space among those buckets. Here value of s is this much, which is little o of n log n. And we throw those all of n items among those buckets. The idea is to figure out which buckets are non-empty. And once we figure out which buckets are non-empty, we then distribute the s amount of space among them. Now recall that here their number of buckets is big O of n, and number of items that are thrown as small of n. Hence, the number of non-empty buckets is at most small of n. And since the space is something bigger than n big of n but smaller than n log n, this space augmentation helps us to achieve the required bounds later. After we figure out which buckets are non-empty, we throw the leftover items into their buckets log n times in parallel. We then remove the duplicates since there are some duplicates due to items are thrown log n times, and then we compact the buckets. We then sort each bucket in quadratic word but optimal span algorithm. We show that with high probability each bucket has height small of log n. Hence we are allowed to use an quadratic word but optimal span algorithm. And thus we get the final sorted array A. We prove the following theorem to incorporate small of n leftover items. We show that with high probability in n, which is the size of the input array A, the unsorted items in set A minus B can be incorporated into the sorted subarray that we get from subset sort in sorted order in n log n work, log n span, and small of n log n space. The final theorem of our overall sorting algorithm is as follows. An array of n items can be sorted with high probability in n in the binary fortune or forking model in n log n work, log n span, and small of n log n space. We now present parallel algorithm for Strasson's matrix multiplication. Before we describe our parallel Strasson's algorithm, let's first review the serial version of the algorithm. There are two input matrices, U and V, and we recursively do the Strasson's matrix multiplication and get output matrix X. At each level of the recursion, we compute the input matrices from its parent level. In this figure, we compute input matrix V2 from its parent level by doing a linear combination between two quadrants V11 and V21. We then recursively multiply temporary input matrices that we got from step 3 here. After that, the temporary output matrices at level I-1 are computed as a linear combinations of the product at level I that we got from step 4. Recall that while computing the temporary input and output matrices at some level, we do some linear combinations either from the parent level or the child level. And in the binary forking or fork join model, this linear combination takes or log n synchronization cost. Since this is a recursion and there are log n heights, and if we sum up all the synchronization cost across all the levels, the span sums up to order log n log square n. And hence we get an algorithm that achieves all the optimal work n to the power w, where w is log base 2 of 7, but our span is not optimal, which is log square n. We introduce a technique called single point computation, where all the cells across all the matrices across all the levels can be computed in parallel independently. In the figure here, this cell independently can compute its value from its parent, and this cell independently compute its value from its parent, and like that. Similarly, all the output cells across all the matrices across all the levels can be computed in parallel independently. Here, in this figure, the output cell here can be computed independently from these cells, which can be computed independently again from these cells. Alright, we now have two parallel Strasson's algorithm. In the first one, we achieve optimal work, but our span is increased by log n factor, we achieve log square n span. In the second one, using single point computation, we have achieved log n optimal span, but the work exploded. It becomes n to the power w plus w prime, where w prime is this much. So naturally the question arises whether we can achieve optimal work and optimal span simultaneously in the binary forking or fork join model for Strasson's MM algorithm. In this work, we present two algorithms. In the first one, we got optimal span, but the work increased only by log n factor. In the second one, we achieve optimal work, but the span increased by log n factor. Now I am going to describe this algorithm where we achieve optimal span, but the work increased by log n factor. During single point computation, we perform the input or output matrices at the leaf level directly from the root level, or from the root level directly at the leaf level. Hence, the work exploded because we did that for all the cells across all the matrices across all the levels. Now, instead of doing so, we divide the whole recursion into log n stages. And if we concentrate on a particular stage, we perform single point computation only within that stage. So here in the ith stage, we compute the input matrices at the leaf level of the stage I from the root level of the same stage I. And we chose the stage boundaries such that in every stage we perform n to the power w work, and if we sum up all the spans across all the stages, the stage still log n. We compute the temporary input and output matrices and store them at the stages boundaries between two consecutive stages. That helps us to reuse work. So in total, we perform n to the power w times log n work because there are log n stages, and our span is optimal, which is log n. Similarly, we compute temporary output matrices using single point computation within a particular stage, and we store the temporary output matrices at the stage boundary. So here, if we concentrate on a particular stage, we compute the temporary output matrix at the root level of that stage from the leaf level of the same stage, and the outputs are stored here, which will be used to compute the parent stage of this stage. And like previous case, here there are log n levels, and each stage performs n to the power w work. So to compute output matrices across all levels, we total performs n to the power w times log n work, and the span still remains log n. These are two main theorems that we prove in the paper for Strasson's MM. The first one is the span optimal Strasson's MM algorithm performs n to the power w times log n work in log n span and uses n to the power w space. The work optimal Strasson's MM algorithm performs n to the power w work in log n times log n span and uses n to the power w divided by log n space. We now briefly state the result that we get for first Fourier transform. Using the single point computation technique, we prove that there exists an FFT algorithm that performs O of n times log to the power gn n work in O of log n times log n span and uses O of n space, where gn is less than 2 for all practical values of n and n is less than 10 to the power 10,000. The single point computation technique is general enough such that the technique can be used in Strasson's like MM algorithms and other dynamic programming algorithms such as Floyd-Warshall's all-pair shortest path and optimal polygon triangulation. Here is a summary of our work. We have presented a parallel sorting algorithm with optimal span and work both with high probability in n in the binary forking or Javanmard. The technique used for sorting can potentially be used in solving other problems such as computing convex hull, etc. We have presented parallel Strasson's MM algorithm with optimal span and near optimal work in the binary forking or Javanmard model. The technique used for Strasson's MM can be used in improving span of other algorithms, including FFT and some dynamic programming. I'm concluding my talk here, and thanks for listening.